All right, let's get started. We will talk about the different types of failure theories. And in our lecture handouts in table 8-2, there's a tabulated list of the failure theories and their loading, use of loadings or stress type, and then the material type, and some remarks about the position of the failure locus line compared to the experimentation's data. So right here, the first one we'll discuss is the maximum normal stress, and you can see here that the material in which it is applicable is for brittle materials, and that's the same for the second one. This is the modified Moore, and this modified Moore is also for brittle materials. And the third one that we'll discuss is the maximum shear stress theory, and that's for ductile materials. And another one for distortion energy theory, that's also for ductile materials. And all this from 1 to 4, we have a static stress. And from 5 to 7, these are failure theories for fluctuating stress and also for the material types. These are applicable for ductile materials. So right here we have remarks regarding example if it's slightly conservative or it's a good predictor or things like that. Okay, so there are still many other failure methods or failure criterion that's not listed here, but these are the ones that we will discuss. Okay, so for the first one, we'll discuss the maximum normal stress. This failure theory basically predicts failure when it predicts failure when the principal stresses, recall the principal stresses from the Moore circles, that's labeled as sigma 1, sigma 2, and sigma 3. If all this exceeds or equals the ultimate strength, so let's just write S sub U for the ultimate strength, then it's gonna fail. Okay, so that's how it predicts failure. And since we can have ultimate tensile strength in tension and in compression, and for some materials they have the same ultimate strength in tension and ultimate strength in compression. But there are also other materials such as brittle materials that are not equal. The strength in tension is not actually equal to the strength in compression. And an example of this is concrete. And you have learned this already in ABE161 that concrete is a material that is strong in compression but weak in tension. Okay, and the compression strength or the tensile strength rather is 10% only of the compression strength. So it's not equal. Okay, so for going back again to this maximum normal stress, it just predicts failure when the maximum stresses would exceed the ultimate tensile strength. So what that means is if we draw the Morse circle, and recall that a Morse circle is a plot between the normal stresses and the shear stress. So let's say we have this Morse circle right here, and we have these three principal stresses, right? So we have these three principal stresses. We have sigma 1, sigma 2, and sigma 3. And since these are stresses, right here this is tension, and going to the left is compression, then that means that somewhere along the line there's going to be a value of, or I think let's write it here, or let's draw it here. Okay, so there's going to be a value of SUT. So ultimate strength and tension, and right here, if they're just the same, then this one is ultimate strength in compression. Okay, so what this theory says is that if your maximum stress is outside this boundary, then that's gonna be failure. Okay, so let's uh, shade this portion. That means this is a failed portion or unsafe. So it must be that these principal stresses will only lie inside these boundaries of SUC and SUT. So that's for the Moore circle. But typically, the failure theories or the failure locus line is plotted between two two principal axes. So let's say this is sigma 1 and this is sigma 2, and this is just simply a principal axis. This one is maximum if we are referring to the horizontal axis, and the vertical axis is the minimum. So if we plot a, and by the way, this is also true if you go to the right. If that's positive, then that's tension, and right here is negative, and that's compression. Along the vertical axis, it's also the same. If you go upward, that's tension, and going downward is compression. Okay, so since this is a stress line or an axis about stress, then again there's gonna be some point right here we're in. That's gonna be our SUT, right? Tension, strength and tension, and right here it's also gonna be strength and tension. And in compression, there's also gonna be some point about compression, and also right here, SUC. And if we draw the boundary of this, it will look something like this. So what that means is that if we are inside this region or this bounded area, this is going to be the safe area. And outside this, that's going to be unsafe. And in terms of equations regarding the factor of safety, how do we solve for the factor of safety? It's just simply for the tension. This is N is equal to the strength. That's the ultimate strength all over the stress or the principal stresses right here. So that's just simple. And let's write here tension. And another one could be that we are in this region purely compression. If all our principal axes are negative, then we are in this region, then that's gonna be S. The strength would be in compression. I mean, based on compression divided by the stress. Okay, so recall that the load point, for example, this is our load point, right? And if we project a line from the origin to this load point where it crosses that, and then extend the line, then we can also actually derive, or we can also make equations regarding the factor of safety about this, right? Because this is the load and this one is the strength, and the factor of safety is basically the ratio of the strength all over the load. All right, so now let's move on to the next failure theory, which is the modified Moore. Modified Moore theory. From the word itself, when you say modified Moore, that simply shows that there are still other Moore theory from which it was derived. Okay, so we'll just focus on the modified Moore theory, and Again, this theory is applicable for static loadings and brittle materials. Is I'm gonna draw this, or I'm gonna draw the principal or the plot between principal, I mean between two principal stresses. And what this looks like is this. Okay, so we have this principal axis, sigma 1 and sigma 2, and again, there's going to be some value of the ultimate tensile strength, and right here, it's going to be ultimate tensile strength. And by the way, the the value of this is just the same because we are referring to the same material. Okay, however, this modified Moore theory is a modification of the Moore's, a column Moore theory. Okay, so this is SUT. So right here along the negative value, we have SUC. And right now I'm going to plot this with a different values for the tension and the ultimate strength in compression. Okay, so let's write this is SU sub C, and also right here that's going to be SU C. Okay, now to plot the failure locus line, so we have a limiting value here, and this one, that's for the first quadrant, and for the third quadrant we'll have a limiting value or a failure locus line of something like this. Okay, the column Moore theory is actually connecting this one, these 2 points, this SUC and this SUT. Okay, it actually connects this, and this is what we call the column Moore. Column Moore theory. This is not yet the modified Moore theory. So the modification is that there's actually a a line or a locus of points wherein the stress state would be purely shear. Okay, and that's going to be the line that's 45 degrees, like this. I think here, let's say 45 degrees. So let's write here line of pure shear, or sometimes they refer to this as shear diagonal or shear diagonal. Okay, so the modified Moore theory actually extends this SUT right here to this point, and this one also extends to this line, and from that line, that's where the from that point, it is connected to the ultimate strength in compression. Okay, so that's why it's called modified Moore theory. Okay, so now we'll have this failure locus line that looks like this. So again, any stress point or stress state outside this bounded region, that's going to be unsafe, and stress state that's inside the bounded region, that's going to be safe. Okay, so the question now is, how do we compute for the normal, sorry, not the normal stress, but rather the factor of safety n. Now for the first and second quadrant, it's actually the same as the maximum normal stress, right? But the equation, or there's going to be changes in the equations when we are in this quadrant. Actually, in this region right here, in this portion. And if we label, I think we'll label the case. So let's say this is case 1, and this is case 2, right? Case 2. This is also case 2. Okay, so why is it case 2? Simply because it's not in this diagonal line right here. I mean the load point, if it's something or somewhere here, then if we project a load line, that's just going to be the same as the maximum normal stress. But if we are here, if this is our load point, and if we project a load line, then there's going to be changes in the equation. So this is case 2b, and this one's case 2a, right? This one as well is case 2b, and this is case 3. Now for the equation for case 1, the condition, actually this is also in our lecture handouts in table 8-4, equations for the modified Moore theory, and we have case 1, and the condition is that sigma 1 is greater than or equal to sigma 2 is greater than or equal to sigma 3, and that just means that the principal stresses are in tension. Okay, and if that's the case, then the equation for the factor of safety is just simply n is equal to SUT all over sigma 1, and for case 2b, okay, we have also, or let's write also the case 2a and then case 2b. So this case 2, the condition for case 2 is just sigma 1 is greater than or equal to 0, is greater than or equal to sigma 2. So that means that one is positive and one is negative. One principal stress is in tension and the other one is in compression. Now, if that's the case, then you have to check if the ratio of the sigma 2 to sigma 1 is less than or equal to 1, or sigma 2 all over sigma 1 is greater than 1. Because if it's less than or equal to 1, then the equation is just actually the same as the case 1, SUT over sigma 1. But for this one, for the case 2b, this is going to be SUC minus S, strength in tension divided by the product of the strengths. Right, we multiply this to sigma 1, okay, minus sigma 2 all over the strength in compression is equal to 1 over n. Okay, so we have a changes in the equation. And for case 3, the condition is just simply 0 is greater than sigma 1 is greater than or equal to sigma 2. And what that means is that all the principal stresses are in compression, and that's the third quadrant. And for that, the equation would be n is equal to negative SU strength, but this time this is strength in compression divided by the principal stress. Okay, so now we are going to do a sample problem regarding these two failure theories, and this problem is taken from the textbook by Mott et al., and the textbook is Machine Elements in Mechanical Design, and this is an example at page 187. The given data is we have an ultimate strength in tension of 40 ksi and ultimate tensile strength in compression, which is equal to 180 ksi, and we have a principal stress sigma 1 is equal to 15, and another principal stress that is negative 80 ksi. So we are going to use the Moore theory, actually the modified Moore theory, and also I included this, also solve using the maximum normal stress theory and plot the failure locus line and the load line. Okay, so let's do that. And for the solution, the first step is let's draw the Moore's circle, actually for reference only, because we have already the principal stresses, but we are going to draw this for reference only, and this is going to be something like this. Okay, so we have sigma 1 right here, and sigma, actually this is, sorry, let's first draw the sigma 1, and the given sigma 2 is somewhere here, and this is negative 80. This one is 15, right? But since this is a plane stress, then we know that the other principal stress, or the remaining principal stress, is 0. So that's going to be somewhere here. So supposedly this should be sigma 1, sigma 2, and sigma 3, right? But we are referring to the principal stresses of the largest circle. Okay, so that's why sometimes it's just written sigma 1 and the other one is sigma 2, because we are referring to the maximum circle. Okay, so this is 15 ksi and this is 80 ksi. Okay, so now let's try to plot the failure locus line. And for that, I have already prepared, or I have already plotted this failure locus line. So we have the principal axis here, the maximum principal axis, and the minimum principal axis. What I mean by that is this is where we are going to plot the maximum, that's along the x-axis, and the minimum principal value would be along the vertical axis. Okay, so the more theory is the red line right here. So the SUT is 40, the ultimate strength in compression is 180. And we have this shear diagonal right here, and we extend this one, we extend this ultimate tensile strength to this line, right? And we plot the load point, or the stress state, and the stress state is 15, right? This is 15 and negative 80. So for that, this is where it falls. This is 15 and negative 80. Okay, so if we project a line from the origin to the load point and then extend that line, then this is where we are going to fall in this region right here. Okay. Okay, so now let's solve for n. All right, solving now for n, for the factor of safety n, using the modified Moore theory. Okay, so first step is to check the condition. Okay, so sigma 1, we know that sigma 1 is greater than or equal to 0, which means the sigma 1 is positive and the sigma 2 is negative, and therefore this is case 2b. And using now the equation for case 2b, we have this, the ultimate strength in compression minus the ultimate strength in tension, it times the sigma 1, and here the product of this of the ultimate strength, okay, minus sigma 2 all over SUC is equal to 1 over n. Okay, if we substitute the values, let's write it here, 180 minus 40, right, times 15 divided by 180 times 40. Okay, what else? Minus, okay, for the load, that's going to be negative. Actually, when I say load, I'm referring to the principal stress. Negative 80 divided by the SUC, which is what is SUC? This is 180, right? Divide is equal to 1 all over n. Okay, so if you do the computation, what we get is n is equal to 1.36. Okay, so that's the factor of safety. Now, if we try using the maximum normal stress, the n is, right, the factor of safety is n is equal to simply SU. Okay, so going back to the plot, we have, here's our load point, and this will be the boundary of the maximum normal stress, the green one. Okay, and right here it's actually in the ultimate tensile strength. Okay, I guess. So if it's in the ultimate tensile strength, then that's gonna be SUT divided by the sigma 1. Okay, so it seems that if this is the value of the of the ultimate tensile strength, this SUT, then it seems that since this is a line or this is linear, then I think you can also express this in terms of the ratio along the or along this axis. So this length right here divided by the length right here. Okay, so I think that also works because this is a line. Okay, so this is 40 divided by 15, and this will be 2.67. Okay, and we see we have different values for the factor of safety when using modified Moore and when using the maximum normal stress. And by the way, the maximum normal stress is not preferred. It's just being included in the references just for historical reasons. Okay, so I think that's all for this video, and in the next video we will continue our discussion about failure theories for ductile materials, and still we are still in static loadings.